Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins your task. The year 1936 marks the publication of Luogeng's seminal contribution on Waring's problem, a work that propelled advancements in number theory and established Hua as a leading figure in the field. This essay undertakes a comprehensive evaluation of the core claims presented within Hua's paper, examining its arguments, methodology, and conclusions with a critical lens. It delves into the specifics of each section, assessing the validity and impact of its assertions within the context of Waring's problem and its subsequent developments. The focus remains relentlessly on dissecting the internal logic and evidence offered by Hua, placing its contributions within the broader intellectual landscape only where directly and demonstrably relevant to the primary assessment. Section 1 Introduction and Problem Formulation. Hua commences by articulating the central question of Waring's problem for any positive integer k. Does there exist a finite integer k of k, such that every positive integer can be expressed as the sum of at most k of kth powers of positive integers? The paper immediately establishes its ambition not to simply demonstrate existence, which Hilbert had already accomplished, but to refine the quantitative understanding, finding tighter bounds for k of k. The introductory claims assert the paper's intention to provide improved estimates, leveraging techniques hitherto unexplored within the Chinese mathematical tradition, yet firmly grounded in the established European framework of analytic number theory. These opening statements themselves present a dual-claim innovation in application. Coupled with adherence to rigorous methodologies, the evaluation commences with noting the audacious nature of these claims given that Hua was, at the time, working largely in isolation from direct access to the leading European mathematicians. The paper's initial success, therefore, rests on the effective demonstration of this proclaimed synthesis of originality and methodological soundness. His initial exposition of the problem, casting it as a quest for efficient representation using kth powers, is a strategic move. This framing emphasizes computational tractability, implicitly promising a path towards more concrete bounds. Section 2. The circle method and auxiliary functions. This section outlines Hua's application of the Hardy-Littlewood circle method, a cornerstone of analytic number theory. Hua introduces auxiliary functions like f of alpha, defined as the summation from x equals 1 to p of the exponential of 2 pi I alpha x to the power of k, and utilizes them to analyze the generating function representing the number of solutions to the Waring's problem equation. The claims center around the effectiveness of these functions in isolating contributions from major and minor arcs within the unit interval. The evaluation here demands understanding how Hua adapted the standard circle method machinery. Previous applications often involved intricate dissection of the unit interval into infinitely many arcs. Hua's contribution lies in carefully balancing the complexity of the arc decomposition with the need for manageable error terms. Indeed, the effectiveness of the circle method depends fundamentally on the precise estimation of these error terms. Furthermore, Hua implicitly claims that his choice of auxiliary functions is optimal or near optimal within the confines of the chosen method. This is a strong, implicit assertion deserving careful scrutiny. The subsequent development of the literature on Waring's problem reveals that while Hua's functions were highly effective, variations could be explored, leading to further refinements. It becomes clear that the selection of optimal auxiliary functions represents a delicate balancing act, demanding both mathematical insight and computational feasibility. Section 3 Estimation of exponential sums. Central to Hua's approach is the meticulous estimation of exponential sums, in particular, the bounding of the magnitude of f of alpha over the minor arcs. This section presents its key inequalities, which serve as the foundation for controlling the overall error term in the circle method. The claim is that these estimates allow for a significant reduction in the upper bound for k of k, paving the way for a more accurate solution to Waring's problem. The evaluation must focus on the rigor and novelty of these specific bounds. Hewer claims to have achieved tighter estimates than previously available, and the veracity of this determines the overall success of his method. The subtle nature of exponential sum estimates means even seemingly small improvements and have large consequences. Hewer's contribution hinges on his ability to navigate the intricacies of these sums, exploiting subtle cancellation effects to achieve a superior level of control. The novelty of these techniques, compared to established methods, warrants deep examination. Hewer's careful dissection of the minor arcs, coupled with his ingenious use of complex analysis, constitute genuine advancements. Section 4 Major Arc Analysis and Singular Series. Hewer meticulously examines the behavior of the generating function on the major arcs, where the value of alpha is close to a rational number with a small denominator. He derives asymptotic formulas for the contribution from these arcs, involving the singular series, denoted by script s of k, and the integral, denoted by iota of k. The key claim here is that the major arc contribution dominates the overall sum and that the singular series, script s of k, is positive for sufficiently large k, ensuring the existence of solutions to Waring's equation. The evaluation must scrutinize Hewer's treatment of the singular series. Establishing its positivity is crucial to demonstrating that the asymptotic formula is meaningful. If the singular series were zero, it would indicate that the major arc contribution vanishes, and the method would fail. Hewer's analysis of script s of k hinges on delicate arithmetic considerations, including properties of prime numbers and their distribution. The argument that script s of k is positive relies on intricate combinatorial reasoning, ensuring that the contributions from various terms in the series do not cancel each other out. The subtleties involved highlight the depth of Hewer's mathematical insight. Section 5 Derivation of Asymptotic Formula. This section presents the main result, an asymptotic formula for the number of representations of an integer as the sum of kth powers. The formula expresses the number of representations as the product of a singular series, script s of k, the integral iota of k, and a correction term that decreases in magnitude as the integer increases. The claim is that this asymptotic formula holds for a wider range of kth powers than previously established, providing a more precise description of the behavior of Waring's function. The evaluation here centers on the conditions under which the asymptotic formula is valid. Hewer's paper presents specific restrictions on the size of the integer being represented and the magnitude of the exponent kth. The significance of Hewer's contribution lies in pushing these limits further than previous researchers. Assessing the conditions for validity requires a thorough understanding of the error terms arising from the circle method. Hewer's success lies in his ability to control these error terms effectively, allowing him to extend the range of applicability of the asymptotic formula. The subtle nature of these conditions underscores the importance of careful analysis. Section 6 Explicit bounds for G of k. Based on the asymptotic formula derived in the previous section, Hewer presents explicit bounds for G of k, the smallest number of kth powers needed to represent any positive integer. The claim is that these bounds are significantly lower than previously known bounds, representing a major advance in the understanding of Waring's problem. The evaluation must focus on the numerical values of the bounds obtained by Hewer. Comparing these values with those derived by earlier researchers provides a direct measure of the improvement achieved. Hewer's contribution rests on his ability to translate the abstract asymptotic formula into concrete numerical estimates. This involves careful optimization of the parameters involved in the circle method. The derivation of explicit bounds demands a combination of analytical skill and computational dexterity. The historical context is vital in this evaluation. Hilbert's proof of existence was purely abstract. It provided no guidance on the actual size of G of k for any particular kth. Hewer's paper represents a major step towards making the problem computationally tractable providing explicit bounds that could be used to estimate the number of cave powers needed for practical applications. Section 7, refining the bounds for small values. Hugh turns his attention to refining the bounds for g of k for small values of k, such as 2, 3, and 4. The claim is that for these specific cases, it is possible to obtain even tighter bounds than those derived from the general asymptotic formula. The evaluation here focuses on the specific techniques employed by Hugh for these small values of k. These techniques often involve ad hoc arguments tailored to the specific properties of the case powers being considered. For instance, the case k equals 3, which corresponds to representing integers as sums of cubes, requires delicate considerations of cubic residues. Hugh's approach involves a combination of analytical and number-theoretical arguments, exploiting the specific structure of these small cases to achieve superior results. The significance of these refined bounds should be emphasized. While the asymptotic formula provides a general framework, the special cases often demand more refined techniques. Hugh's paper demonstrates the importance of combining general methods with specific insights. Section 8, the singular series and its properties. Hugh dedicates a section to a deeper exploration of the singular series, script S of k, investigating its properties and its connection to the representation problem. He claims that the behavior of the singular series is intimately linked to the solvability of Waring's equation, and that its positivity is a necessary condition for the asymptotic formula to hold. The evaluation should focus on Hugh's arguments regarding the positivity of the singular series. This is a critical point, as the entire approach hinges on the assumption that script S of k does not vanish. Hugh's proof involves intricate combinatorial arguments, considering the possible values of the kth powers modulo various primes. The subtleties involved highlight the depth of the connection between number theory and the representation problem. Hugh's analysis of the singular series is a masterpiece of mathematical reasoning. It demonstrates the power of combining analytical techniques with deep number-theoretical insights. His work on the singular series became a cornerstone of subsequent research in Waring's problem. Section 9, applications and further refinements. Hugh explores potential applications of his results and discusses avenues for further refinements. He claims that his estimates can be used to improve bounds for other related problems in additive number theory, and that further research could lead to even tighter bounds for g of k. The evaluation here centers on the extent to which Hugh's claims have been borne out by subsequent research. Did his techniques indeed prove useful in solving other problems? Did later researchers succeed in improving upon his bounds for g of k? The historical record shows that Hugh's methods have indeed had a lasting impact on the field. His techniques have been adapted and extended to solve a wide range of problems in additive number theory. Furthermore, his bounds for g of k have been steadily improved over the years, though many of the fundamental ideas can be traced back to Hugh's original work. Hugh's paper serves as a foundation for future work in this area. Section 10, comparison with existing results. Hugh provides a detailed comparison of his results with existing work on Waring's problem, highlighting the improvements he has achieved and acknowledging the contributions of earlier researchers. The claim is that his work represents a significant advancement over the state of the art, providing both tighter bounds and a more detailed understanding of the problem. The evaluation here must assess the accuracy and fairness of Hugh's comparison. Were his claims of improvement justified? Did he accurately represent the contributions of his predecessors? A careful examination of the historical record reveals that Hugh's assessment was largely accurate. His bounds were indeed tighter than those previously available. He acknowledges Hilbert's existence proof and makes improvements upon Hardy and Littlewood's formulation. Section 11, methodological considerations. Hugh reflects on the methodological aspects of his approach, discussing the strengths and limitations of the circle method and suggesting alternative approaches that could be explored in future research. The claim is that while the circle method is a powerful tool, it is not without its limitations, and that further progress may require the development of new techniques. The evaluation must consider Hewer's reflections on the limitations of the circle method. What are the inherent challenges in applying this method to Waring's problem? Are there alternative approaches that might overcome these challenges? Contemporary research reveals that while the circle method remains a central tool in additive number theory, it has been augmented by other techniques, such as the sieve method. Hewer's recognition of the method's limitations reflects his deep understanding of the mathematical landscape. Section 12, the Hewer inequality and its consequences. While not explicitly titled as such in the original paper, the essay's analysis would be incomplete without recognizing the implicit emergence of what becomes known as the Hewer inequality. Throughout the estimations of exponential sums, Hewer implicitly demonstrates a powerful inequality which bounds the integral of the magnitude of f of alpha raised to the power of 2j, where j is a positive integer, over the unit interval. This inequality, subsequently named after him, provides a crucial tool for bounding the contribution from the minor arcs in the circle method. The claim is that this implicit inequality is a powerful and versatile tool, applicable to a wide range of problems in additive number theory. The evaluation requires recognizing the significance of this implicit contribution. While Hewer does not explicitly formulate this inequality as a standalone result, its repeated application throughout the paper demonstrates its inherent importance. Subsequent research has recognized the generality and utility of this inequality, formalizing it and applying it to various other contexts. The Hewer inequality has become a standard tool in the arsenal of number theorists. Section 13, Diophantine equations and Waring's problem. Hewer's treatment of Waring's problem is intrinsically linked to the study of Diophantine equations. He utilizes the circle method to analyze the density of solutions to the equation x1 to the power of k plus x2 to the power of k plus and so on plus xk to the power of k equals n, where x1, x2, and so on xk are positive integers and n is a given integer. The claim is that understanding the solutions to this Diophantine equation sheds light on the properties of Waring's function, g of k. The evaluation must focus on the connection between Diophantine equations and Waring's problem. Hewer's approach demonstrates the power of viewing Waring's problem as a problem in Diophantine analysis. By analyzing the solutions to the associated Diophantine equation, he is able to derive valuable information about the representation of integers as sums of kth powers. The interplay between Diophantine analysis and additive number theory is a central theme in Hewer's work. Section 14, the influence of Vinogradov. While Hewer's work is undoubtedly original, a key aspect is the clear influence of Ivan Matveyevich Vinogradov. Explicitly, Hewer's refined estimates of exponential sums and his handling of the major and minor arcs bear a strong resemblance to Vinogradov's techniques. The claim here is that Hewer's success owes a significant debt to the ideas and methods pioneered by Vinogradov, adapted and extended to the specific context of Waring's problem. The evaluation should assess the extent of Vinogradov's influence on Hewer's paper. Did Hewer simply apply Vinogradov's methods directly, or did he make significant adaptations and improvements? A careful examination of the technical details reveals that Hewer indeed made significant contributions, building upon Vinogradov's foundation. While the overall framework of the circle method and the techniques for estimating exponential sums are clearly inspired by Vinogradov, Hewer's specific estimates and his handling of the singular series are original contributions. Section 15, the legacy of Hewer's work on Waring's problem. Hewer's paper has had a lasting impact on the field of number theory, shaping the direction of research on Waring's problem for decades to come. His work forms the foundational core for subsequent investigations. The claim is that Hewer's work not only provided improved bounds for g of k, but also established new techniques that transformed the field. The evaluation should focus on the long-term impact of Hewer's work. How has it influenced subsequent research on Waring's problem and related areas? The historical record demonstrates that Hewer's influence has been profound. His techniques have been adapted and extended to solve a wide range of problems in additive number theory. Furthermore, his emphasis on explicit bounds and his meticulous analysis of the singular series have become hallmarks of the field. Luogeng's unwearing's problem stands as a significant contribution to number theory, providing improved bounds for Gay of K and introducing novel techniques. The originality and rigor of Hue's arguments, particularly his refinement of exponential sum estimates and his meticulous analysis of the singular series, mark a substantial advancement, while acknowledging the influence of earlier work, particularly that of Vinogradov. Hue's paper demonstrates independent ingenuity. In conclusion, Hue's work has shaped the direction of research on Waring's problem, solidifying his place as a leading figure in 20th century mathematics. The paper remains a testament to the power of analytical number theory and a source of inspiration for future generations of mathematicians.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.